Please subscribe to support the channel. The question, what's above and below our solar system, reminds us that space isn't flat. It's a vast, three-dimensional expanse. Our solar system lies in a thin disk called the ecliptic plane, and even that disk sits within a much larger one, the galactic plane of the Milky Way. When we say above or below, we're talking about directions relative to these planes, not absolute positions, because in space, there's no true up or down. Still, exploring what lies beyond our solar system in every direction helps us understand our motion, our place in the galaxy, and the grand structure of the cosmos itself. As we begin to explore what lies above and below our solar system, the next step in our cosmic journey is to understand exactly where we are in the grand structure of the universe, our cosmic neighborhood. Just as every home has an address, our solar system too occupies a specific location in the immense galactic city that is the Milky Way. When we look up at the night sky, we're not simply gazing at random points of light scattered across blackness. We're looking from within a vast spiral galaxy, a colossal rotating disk made of hundreds of billions of stars, clouds of gas and dust, and mysterious dark matter forming its invisible backbone. Our galaxy, the Milky Way, is a barred spiral galaxy stretching about 100,000 light-years across. It's shaped like a giant pinwheel, with a dense central bulge of old stars and the bar of stellar material cutting across its heart, from which long curving spiral arms extend outward like elegant ribbons. Our Sun and all its planets reside in one of those spiral arms, a smaller one called the Orion Arm or Orion Spur. This region is not one of the galaxy's main arms, like the Perseus Arm or the Sagittarius Arm, but rather a minor offshoot, a sort of bridge connecting them. Even though it's small in galactic terms, it's enormous beyond human comprehension, stretching for thousands of light years and hosting countless stars, nebulae, and star-forming regions. In this grand structure, our solar system is located roughly 27,000 light-years from the galactic center, about halfway between the heart of the Milky Way and its outer rim. If we could somehow leave the galaxy and look back from afar, we'd see the Milky Way as a glowing disk of light, slightly tilted with swirling arms full of stars and dark dust lanes weaving through them. Somewhere along one of those arms, faint, almost invisible to the naked eye, is a small yellow star we call the Sun. From that cosmic perspective, our entire solar system would appear no larger than a grain of dust suspended in a luminous spiral of billions of suns. Within this Orion Arm lie the neighborhood filled with familiar constellations, Cygnus, Aquila, Perseus, and Orion, the last of which gives our arm its name. The Orion Arm is not static. It's a region of vibrant cosmic activity, a nursery for new stars. Clouds of hydrogen gas collapse under gravity, igniting nuclear fusion and giving birth to brilliant new suns. The Orion Nebula, for example, located about 1,300 light-years away, is one of these stellar nurseries and a jewel of our local region. It's part of a grand tapestry that includes dark clouds, open star clusters, and massive molecular regions, all ingredients of galactic evolution. When we speak of the solar system's position in this spiral arm, we're not talking about a fixed point. Everything in the Milky Way moves, slowly, gracefully, but ceaselessly. Our solar system orbits the galactic center at a speed of about 220 kilometers per second, taking roughly 230 million years to complete one full revolution. That means since the formation of the Earth about 4.5 billion years ago, our world has made only about 20 trips around the galaxy. During each orbit, the solar system drifts through different regions, passing through clouds of interstellar gas, approaching and moving away from star clusters and weaving between arms of the galactic spiral. Our position is also shaped by the invisible matter that surrounds us. The Milky Way is embedded in a halo of dark matter, a mysterious, unseen substance that exerts gravitational influence on everything in the galaxy. This halo extends far beyond the visible stars, enveloping the galactic disk like a massive sphere. Inside this gravitational domain, our solar system moves not just around the galactic center, but also slightly above and below the galactic plane, following a wave-like motion that gives us a sense of vertical movement through the galaxy. If we could map our surroundings in 3 dimensions, we'd see that our neighborhood isn't empty. Within just a few dozen light-years of the Sun lie hundreds of other stars, some with planets, some without. Stars like Alpha Centauri, Barnard Star, Proxima Centauri, Sirius, and Epsilon Eridani share the same galactic neighborhood. They too orbit the Milky Way center, each tracing its own path through the spiral arms. Collectively, these nearby stars form what astronomers call the local stellar neighborhood, and together with nearby gas clouds and interstellar dust, it defines the local environment of our solar system within the galaxy. Zooming out further, our solar system sits inside a region of space known as the local bubble, a vast cavity of low-density superheated gas thought to have been carved by ancient supernova explosions. This bubble spans about 1,000 light-years and contains fewer interstellar clouds than average, allowing light from distant stars to travel through relatively unobstructed. The local bubble itself is part of an even larger network of similar bubbles, which interconnect like cosmic soap foam across the galaxy. The Orion Arm, our broader home, threads through these structures, forming the landscape through which our sun moves. In galactic coordinates, a special system astronomers use to describe positions in the Milky Way, our solar system is slightly above the galactic midplane, hovering around 20 light-years north of the central disk. This offset may seem small, but on the scale of the galaxy, it's like being a few centimeters above the Earth's surface. Over millions of years, the Sun oscillates up and down through this plane in a smooth, cyclical motion, driven by the gravitational pull of the Milky Way's mass. These oscillations define part of the answer to what's above and below, a topic we'll explore in detail soon. But for now, it's essential to understand that our solar system's location inside the Orion Arm, orbiting the galactic center, and floating within the local bubble, defines the framework of our cosmic neighborhood. Everything we see in the night sky, from the Milky Way's hazy band to the familiar constellations, is shaped by this position. The bright streak across the heavens that we call the Milky Way is not some distant galaxy. It's the view from within our own. We're looking edge-on through our galactic disk, peering through layers of stars, dust, and glowing nebulae that mark the spiral structure of our home. It's humbling to realize that in galactic terms, we inhabit a quiet suburb far from the bustling, energetic core of the Milky Way. The galactic center, with its dense star clusters, swirling gas clouds, and a supermassive black hole known as Sagittarius A, lies tens of thousands of light-years away. Out here in the Orion Arm, things are relatively calm. It's a region stable enough for life to evolve, protected from the chaotic radiation and gravitational disruptions that dominate closer to the center. In a sense, our location may not be random. It might be part of why life on Earth was able to emerge and persist for billions of years. Our cosmic neighborhood, then, is both familiar and incomprehensibly vast. It's where our solar system, one of countless in the Milky Way, continues its endless voyage through the galactic sea. It's a neighborhood defined not by borders or cities, but by gravitational boundaries, interstellar clouds, and the silent presence of countless stars drifting beside us on their own journeys.
And as we understand where we are within this enormous spiral, we can begin to explore the finer structures that define our movement, the planes that organize celestial motion, giving meaning to the words above and below. To grasp those next layers of cosmic geometry, we'll turn now to the foundation of our own system, the solar system's plane, the thin, flat disk where planets dance around the sun, setting the stage for everything that lies above and below it. Now that we've placed our solar system within its grand galactic neighborhood, it's time to zoom back in and examine the structure of our own immediate home, the framework that defines where above and below actually begin to have meaning for us. This framework is what astronomers call the solar system's plane, a vast, invisible, and elegantly organized disk known as the ecliptic plane. When we picture the solar system, we often imagine the sun at the center and the planets orbiting around it like marble circling a glowing campfire. What's remarkable, however, is how orderly those orbits are. Nearly all the planets, from tiny Mercury to giant Neptune, move along roughly the same flat surface, as if the entire solar system were built upon a cosmic sheet. This shared alignment isn't a coincidence. It's a remnant of our solar system's birth nearly 4.6 billion years ago. In the beginning, the sun and its planets formed from a gigantic cloud of gas and dust known as the solar nebula. Under the pull of gravity, this nebula began to collapse inward, spinning faster as it shrank, much like a figure skater pulling in their arms to spin more rapidly. As the cloud rotated, its material flattened into a rotating disk around the forming sun, with most of the matter concentrating along that central plane. From this thin, spinning sheet of gas and dust, planets, moons, asteroids, and comets eventually took shape. The legacy of that process is what we now call the ecliptic plane, the flat disk-like region in which nearly every major object in our solar system continues to orbit to this day. If we could look at the solar system from far above its north pole, we'd see a breathtaking sight: the sun blazing at the center, and around it, the orbits of Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune stretched out like concentric rings of light, all lying within a thin slice of space only a few degrees thick. This immense cosmic platter, spanning billions of kilometers across, is what keeps our solar system's geometry so stable and recognizable. Even the dwarf planets, Pluto, Eris, and Haumea, though slightly tilted, follow paths that still trace the same general plane. This alignment defines the baseline for everything else in our local cosmos. When astronomers refer to something being above or below the solar system, what they mean is that the object lies above or below this ecliptic plane. It's our local version of up and down. For instance, when we talk about the moon rising north or south of the sun's path across the sky, or when comets dive toward the inner solar system from unusual angles, we're describing their positions relative to the same reference plane. The ecliptic plane also serves as the backdrop for one of the most familiar patterns in our sky, the zodiac. The 12 constellations of the zodiac trace the apparent path of the sun, moon, and planets through the heavens, a direct result of their shared movement along this flat disk. Ancient astronomers, long before understanding orbital mechanics, noticed that the planets never strayed far from this narrow celestial belt. What they were actually observing was the projection of the solar system's plane onto the dome of the sky, the ecliptic itself. The ecliptic plane is not a perfect, rigid surface, however. Each planet's orbit is slightly tilted or inclined relative to it. Mercury's orbit, for instance, is tilted by about 7 degrees, while Earth's is almost perfectly aligned, and Pluto's by a dramatic 17 degrees. These small inclinations create subtle variations in how each planet moves relative to the sun's apparent path across the sky. When two orbits cross each other's planes, the difference in inclination determines whether one planet orbits slightly above or below another at any given moment in space. It's important to note that above and below are not absolute directions. They depend entirely on the orientation of this plane. In the cosmic sense, there's no universal up or down. These are relative terms, meaningful only within a chosen frame of reference. For the solar system, that frame is the ecliptic. From Earth's point of view, the north side of the plane points toward a specific region of the sky, roughly toward the constellation Draco, while the south side points toward Doradus. This orientation provides astronomers a way to describe the three-dimensional layout of our local space with precision and consistency. The stability of the ecliptic plane also shapes the architecture of other solar system structures. The asteroid belt, located between Mars and Jupiter, follows this same plane, as does the Kuiper belt, a distant ring of icy bodies beyond Neptune. Even the Oort cloud, the vast spherical shell of icy debris that marks the outer boundary of the Sun's influence, traces its origins back to this flattened disk, though over billions of years, gravitational interactions have scattered its contents into a more spherical distribution. Because everything in the solar system formed from the same rotating nebula, this alignment has persisted for eons. Yet it's not perfectly static. Gravitational nudges from giant planets and passing stars slowly perturb orbital inclinations. Over immense timescales, this causes planets and smaller bodies to drift slightly above or below the ecliptic plane, creating gentle oscillations in their motion. Despite these minor wobbles, the system remains remarkably flat, a cosmic disk of motion and order amid the chaos of space.
Interestingly, this same concept of a flattened plane repeats itself on grander cosmic scales. Just as the solar system is structured as a thin disk of orbits around the Sun, our Milky Way galaxy is also a flattened disk of stars orbiting its central bulge. The solar system's ecliptic plane is tilted by about 63 degrees relative to the Milky Way's galactic plane. This means that if you could see both planes overlaid in space, they wouldn't align. Instead, they'd intersect at an angle, each defining its own up and down. This difference becomes essential when we begin to explore what lies above and below the solar system from a galactic perspective. Because what's above in solar terms might not be above in galactic terms at all. To visualize this, imagine holding a spinning coin at a tilt while standing on a large rotating record. The coin's plane represents the ecliptic, while the record's surface represents the galactic plane. Both are flat and circular, but they're oriented differently, each with its own unique axis and direction. The planets follow their orbits along the tilted coin, while the entire coin itself, or solar system, moves along the broader sweep of the galactic record. Understanding this relationship is the key to bridging our local view of above and below with the galactic one. So, when we ask what lies above or below our solar system, our first answer lies here, within this elegant disk of motion. Above the ecliptic plane are regions of space where objects orbit at higher inclinations, such as certain comets or asteroids whose tilted paths carry them far north of the Sun's equatorial plane. Below it, we find orbits inclined in the opposite direction, sweeping beneath the solar system's primary layer. To an observer outside the system, these objects would appear to weave in and out of the flat band defined by the planets, like sparks dancing above and below a spinning wheel of light. This understanding gives us a foundation, a kind of gravitational horizon from which all celestial directions can be defined. The ecliptic plane is our local reference, the stage on which every planetary orbit plays its part. Yet, beyond this local geometry lies a much larger structure, the galactic plane, the disk of the Milky Way itself, which defines the next scale of above and below. To truly grasp our solar system's place in the universe, we must now rise beyond our Sun's domain and look outward to the vast, luminous plane of our galaxy, the greater stage upon which our entire solar system performs its timeless dance. Having established the solar system's own flat, elegant structure, the ecliptic plane, we can now step back and expand our perspective to a much grander scale, the plane of our galaxy itself. Just as the planets orbit the Sun within a thin disk, the Milky Way galaxy also organizes itself into a vast disk-shaped structure where the majority of its stars, gas, and dust reside. This is known as the galactic plane, a cosmic stage of unimaginable scale that stretches tens of thousands of light years across, defining the overall geometry of our galactic home. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped concentration of stars with sweeping spiral arms radiating outward. Its galactic plane is the flat disk in which these arms lie,
along with most of the galaxy's visible stars and dense interstellar clouds. This disk isn't infinitely thin. In fact, it has a thickness of roughly 1,000 light-years near the Sun's location, and it becomes denser and thicker toward the galaxy's center. Embedded within it are star clusters, nebulae, and enormous molecular clouds, all orbiting the galaxy's central mass like planets in a grand cosmic carousel. In comparison, the solar system's ecliptic plane is minuscule, a mere slice of this massive galactic pancake. When we talk about above or below in a galactic sense, we are referring to positions relative to this plane. Most of the galaxy's activity, star formation, spiral arm structure, and the majority of stellar orbits occurs within or very near this plane. The disk is a dynamic, bustling environment. Stars move in roughly circular paths around the galaxy center, gas clouds orbit and collide, and spiral arms propagate as wave densities, compressing gas and triggering bursts of star formation. The disk is the heart of the galaxy, its luminous spine stretching across the cosmos and shaping the environment of every star within it, including our Sun. However, the solar system itself is not perfectly flat within the galactic plane. While the galaxy defines a kind of midline or reference plane, our Sun currently hovers about 20 light-years above this central plane. This might seem small, but in galactic terms, it places us slightly north of the galactic midline. Moreover, the Sun and solar system oscillate in a gentle up and down motion as they orbit the galactic center, moving above and below the plane over cycles of roughly 30 million years. This oscillation is caused by the gravitational pull of the galaxy's combined mass, a slow vertical bobbing as the solar system glides along its orbit around the center. The galactic plane also serves as a reference frame for astronomers when mapping the positions of stars, gas clouds, and other cosmic structures. By defining coordinates relative to the galactic plane, along with the galactic center and galactic poles, scientists can describe locations in three-dimensional space across the galaxy. This system, known as galactic coordinates, helps us make sense of the Milky Way's vastness, and it allows us to locate objects not just in the sky as we see them from Earth, but in their actual positions relative to the galactic's flat disk. Even within this plane, the distribution of stars is not perfectly uniform. The central bulge is thick and crowded with older stars, while the spiral arms are thinner, populated with younger stars and glowing nebulae. Dust lanes wind through the disk, obscuring parts of the galaxy and creating dramatic contrast when viewed from telescopes. The plane is active, alive with motion, yet it still maintains the general flatness that allows us to talk meaningfully about above and below in galactic terms. Outside the disk lies the galactic halo, a roughly spherical region populated by ancient stars, globular clusters, and dark matter. This halo extends far above and below the galactic plane, a subtle but massive component of the Milky Way that influences the motion of stars and the structure of the galaxy itself. The contrast between the thin, active disk and the expansive halo highlights how the galactic plane serves as the reference point, the dividing line between above and below on a truly cosmic scale. Our solar system's slight offset from the galactic plane means that even on this grand scale, we occupy a position that is never perfectly aligned. This misalignment may have profound implications. By being slightly above the denser midplane, we are somewhat shielded from the most intense regions of star formation, supernova explosions, and gravitational perturbations that dominate the central disk. This quiet position could be one factor that has allowed life to persist on Earth for billions of years. The concept of the galactic plane also bridges our understanding of local and cosmic scales. Just as the ecliptic plane organizes our solar system and defines directions like above and below, the galactic plane provides a broader reference, contextualizing the solar system's position relative to hundreds of billions of stars. In a way, it's like moving from a neighborhood street map to a city atlas. The same principles of direction apply, but the scale and complexity are magnified beyond imagination. Understanding the galactic plane sets the stage for appreciating the solar system's motion through the Milky Way, and how that motion traces a wave-like path above and below this plane. It also gives us the framework to describe neighboring stars, interstellar clouds, and even the more distant structures that lie well outside the disk. When we look above or below from a galactic perspective, we are considering a distance measured not in billions of kilometers, but in thousands of light years across the luminous expanse of the galaxy. In summary, the Milky Way itself has a disk-shaped plane, a cosmic sheet teeming with stars, gas, and dust spinning gracefully around the galactic center. The solar system resides slightly above this plane, never perfectly flat within it, oscillating gently in a vertical rhythm as it orbits the galaxy. This plane provides a reference for above and below on a galactic scale, just as the ecliptic plane does for our solar system. Together, these two planes, one local, one galactic, form the backbone of our understanding of direction in space, giving structure to the seemingly chaotic vastness of the cosmos and preparing us to explore the vertical architecture of our neighborhood, what truly lies above and below. With the galactic plane established as the broader reference for above and below, we can now examine how our solar system navigates this enormous structure. Far from being stationary, the Sun and its planetary family are in constant motion, tracing a complex path through the Milky Way. While we often simplify this motion as a circular orbit around the galactic center, the reality is far more intricate. The solar system actually moves in a wavy up and down trajectory relative to the galactic plane, oscillating above and below it as it orbits the galaxy's center. The solar system's orbit around the Milky Way is immense in scale. It takes roughly 230 million years to complete a single revolution, a period sometimes called a galactic year. During this journey, the Sun travels at an astonishing speed of approximately 220 kilometers per second, or roughly 490,000 miles per hour. This rapid motion allows the solar system to complete about 20 orbits since the Earth formed 4.6 billion years ago. While the orbit is roughly circular when projected onto the plane of the galaxy, it is not a simple flat circle. Gravitational interactions with the Milky Way's mass, the combined pull of stars, gas, dust, and the mysterious dark matter halo, induce a gentle vertical oscillation, causing the solar system to rise above and below the galactic midplane in a continuous wave-like motion. This up and down movement can be likened to a boat riding the swells of a vast ocean. As the solar system moves forward along its orbital path, it experiences peaks and troughs relative to the galactic plane. The amplitude of this motion is modest on a cosmic scale. The Sun currently sits about 20 light-years above the plane, yet it's enough to periodically shift the solar system into regions of slightly higher or lower stellar density. Each full oscillation, from maximum height above the plane to maximum depth below it and back, takes roughly 60 million years, meaning the solar system has undergone dozens of these vertical cycles over its lifetime. The reason for this motion lies in gravity. While the Milky Way's mass is concentrated primarily in its disk and central bulge, it also extends above and below the disk in the form of a diffuse stellar halo and a pervasive dark matter halo. This distribution of mass exerts a vertical gravitational pull on the solar system, much like a spring trying to return a displaced object to equilibrium. When the Sun moves above the galactic plane, gravity pulls it downward. When it passes below, gravity draws it back upward. The result is a smooth, oscillating path, a cosmic wave that carries the solar system above and below the densest regions of the galactic disk. This up and down movement has profound implications for the solar system and Earth itself. Some researchers speculate that periods when the solar system passes closer to the galactic plane, where stellar density and interstellar clouds are higher, may coincide with increased comet activity from the outer solar system. The gravitational tug of nearby stars or denser gas clouds could perturb distant objects in the Oort cloud, sending comets hurtling toward the inner solar system. Over geological timescales, this could influence the frequency of impacts on Earth, potentially affecting life. While these ideas remain under study, they highlight how the solar system's motion through the galaxy is not just a matter of abstract mechanics, it may have tangible effects on our planet. The solar system's oscillation also provides a sense of perspective on the terms above and below. From the standpoint of the ecliptic plane, above and below are relative to the Sun and its planetary plane. But from the galactic perspective, above means north of the galactic plane, and below means south of the galactic plane. Because a solar system rises and falls through this plane, the designation of above or below is itself temporary, constantly shifting as we glide along our orbit. This dynamic aspect reminds us that the cosmos is not static. The universe is a moving, evolving system, and our solar system is a participant in a continuous dance of gravitational forces. The oscillation is gentle but consistent. The amplitude is small compared to the radius of the sun's galactic orbit, tens of light years compared to 27,000 light years from the center, yet it's measurable, and astronomers can track it using the motions of nearby stars. By modeling the gravitational potential of the Milky Way's disk and halo, scientists can predict the sun's vertical position at different points in its orbit, allowing us to reconstruct its past trajectories and anticipate future movements through the galaxy. This wavy motion is just one layer of structure in the Milky Way, highlighting the intricate choreography of stars within a galaxy. In addition to vertical oscillation, the solar system exhibits slight radial deviations as it orbits a center. The path is not a perfect circle. It is slightly elliptical, influenced by variations in the mass distribution of the galaxy, such as spiral arms and nearby massive molecular clouds. These deviations contribute to small shifts in the solar system's speed and position, adding complexity to its journey through the galactic disk. Despite this, the general pattern remains a smooth, wave-like trajectory, with the sun rising and falling above and below the galactic plane in a rhythm that has persisted for billions of years. Understanding this motion helps us contextualize what lies above and below on a galactic scale. Stars, gas clouds, and other structures that reside above the galactic plane may at times be nearer or farther from us depending on where we are in our vertical oscillation. Similarly, structures below the plane, including regions rich in gas or neighboring stellar populations, are sometimes closer or more distant. This three-dimensional movement emphasizes that the Milky Way is not a static two-dimensional disk, but a dynamic, pulsating system, with the solar system tracing a path that spans both vertical and horizontal dimensions. Our wavy orbit also bridges the understanding between local and galactic scales. On the local scale, planets oscillate slightly above or below the ecliptic plane, creating inclinations in their orbits. On the galactic scale, the solar system itself oscillates above and below the galactic plane, showing that oscillatory motion is a recurring theme in cosmic dynamics. Gravity, rotation, and the distribution of mass together shape these movements, and by studying them, we gain insight into the broader patterns governing the motion of stars within the Milky Way. In essence, the solar system's motion through the galaxy is a delicate rhythmic journey. As it orbits a galactic center at breathtaking speeds, it rides a gentle wave, drifting above and below the dense disk, sweeping past stars, clouds, and unseen dark matter. This oscillation defines a living, moving up and down, providing the framework for understanding what lies in the galactic north and south, the regions above and below the Milky Way. It is this motion, subtle yet continuous, that sets the stage for exploring the specific structures and stellar neighbors that occupy the spaces above and below our solar system, giving true meaning to the question that began our journey: what exists beyond the familiar orbits of our planetary family?
Having explored the solar system's wave-like motion through the galactic plane, we can now turn our gaze toward what lies above the solar system in a galactic sense. In astronomical terms, above corresponds to the direction pointing north of the Milky Way's plane, a point in the sky known as the North Galactic Pole. This isn't just a vague notion. It's a precisely defined direction based on the orientation of the Milky Way's disk, providing a fixed reference for mapping the galaxy in 3 dimensions. From Earth, the North Galactic Pole is located roughly in the direction of the constellation Coma Berenices, a relatively faint constellation whose name translates to Berenice's hair, evoking the delicate trails of stars that decorate the northern sky. Looking up toward the North Galactic Pole is like looking out from the solar system into the quieter vertical dimension of the Milky Way. Unlike the densely packed disk of stars, gas, and dust that dominates the plane, this direction extends into regions of lower stellar density, allowing us to peer deeper into the galactic halo and beyond. Stars become more sparsely distributed, and the light from the Milky Way spiral arms fades, giving way to the subtle glow of more distant stars and galaxies. It is along this axis that astronomers can study structures not constrained by the disk's plane, such as globular clusters, high-latitude gas clouds, and the intricate filaments of the galactic halo. The North Galactic Pole is not empty, though. Above the plane, the halo contains stars of great age, some nearly as old as the galaxy itself. These stars move in elongated, elliptical orbits that can take them far above the disk, occasionally bringing them closer to the solar system before returning to the galactic outskirts. Interspersed among them are globular clusters, dense, spherical groups of hundreds of thousands of stars that trace the galaxy's ancient history. Their presence above the plane reminds us that the galaxy is not merely a flat spiral, but a three-dimensional system, with layers and structures extending vertically far beyond the disk we see in the night sky. Gas and dust are also present above the plane, though much less densely than within the disk. The interstellar medium thins as one moves toward the galactic poles, consisting primarily of diffuse hydrogen and helium. This lower density allows high-energy cosmic rays to travel more freely, influencing the local radiation environment and shaping the way magnetic fields thread through space. Observations in X-ray and ultraviolet wavelengths reveal bubbles of hot gas rising from the disk into the halo, evidence of ancient supernovae and stellar winds venting material into the vertical dimension. When we look toward Coma Berenices, we are effectively peering along the axis of the Milky Way's north, following the direction in which the solar system is slightly displaced above the midplane. This direction provides a natural coordinate for studying objects that are not part of the dense, star-rich disk. Many satellite galaxies of the Milky Way, including the Sculptor and Leo groups, are positioned at higher latitudes. Lying above or below the plane, their orbits tracing long paths influenced by the galaxy's gravity. Observing upward toward the North Galactic Pole thus gives astronomers a unique vantage point to understand both the local environment and the broader cosmic architecture. The North Galactic Pole also has practical applications. Astronomers use it as a reference in the galactic coordinate system, a spherical coordinate system with the galactic center as the origin. Galactic latitude is measured as the angle above or below the plane, with plus 90 degrees pointing directly toward the North Galactic Pole. This makes it easier to chart the positions of stars, nebulae, and other cosmic structures relative to the Milky Way, providing a standardized way to describe the three-dimensional structure of our galaxy. In terms of neighboring stars, looking above the plane in the direction of Coma Berenices means considering stars that lie slightly outside the dense disk, forming a population that is less influenced by the gravitational tides and collisions prevalent within the spiral arms. Some of these stars may belong to the galactic halo, moving in highly inclined orbits, while others may trace trajectories connected to past galactic mergers, remnants of dwarf galaxies absorbed by the Milky Way over billions of years. These populations provide astronomers with crucial clues about the galaxy's formation history and the evolution of its structure. Even at these higher latitudes, interstellar phenomena are present. Faint clouds of gas and dust rise above the disk, part of the diffuse interstellar medium, while energetic processes from the galactic disk, including supernova explosions and powerful stellar winds, project material upward, forming loops, arcs, and bubbles that extend for hundreds of light years. Observing in multiple wavelengths, from radio to X-ray, reveals a rich interplay of matter and energy above the plane, demonstrating that even regions of lower stellar density are far from empty. Looking upward from the solar system thus provides a remarkable contrast to our position within the galactic disk. In the plane, stars are tightly packed, nebulae glow brightly, and spiral arms trace intricate patterns of ongoing star formation. Above the plane, the environment is quieter, more diffuse, and ancient, a combination of old stars, globular clusters, tenuous gas, and magnetic fields. This vertical dimension, the direction of the North Galactic Pole, is a vital part of the galaxy structure, revealing how the Milky Way is not simply a flat spiral, but a layered three-dimensional system with dynamic motion in every direction. By understanding the above direction, we gain perspective not only on the galactic halo and its constituents, but also on the cosmic neighborhood beyond our immediate spiral arm. Objects above the plane include distant stars and clusters, high-latitude gas clouds, and even satellite galaxies that orbit the Milky Way. All of these elements help define the three-dimensional structure of the galaxy and provide context for the solar system's position within it. In essence, looking above the solar system is looking toward the North Galactic Pole, along a line of sight towards Coma Berenices, into a quieter, less crowded region of the galaxy. It's a direction that leads out of the luminous spiral disk and into the galactic halo, offering a view of ancient stars, globular clusters, tenuous gas, and distant satellites. This vertical perspective, combined with our understanding of motion and the galactic plane, allows us to appreciate the three-dimensional nature of the Milky Way and sets the stage for exploring what lies in the opposite direction, below the solar system, toward the South Galactic Pole. Having explored the northern reaches of the galaxy above the solar system, we now turn our attention below the galactic plane. In galactic terms, below points toward the South Galactic Pole, a direction roughly aligned with the constellation Sculptor, while above carries us toward the quieter halo regions near Coma Berenices. Below offers a complementary view into the southern vertical dimension of the Milky Way, revealing a similarly complex but distinct environment of stars, clusters, and interstellar material that exists beneath the plane of the galactic disk. From Earth, the South Galactic Pole lies far from the dense star-filled regions of the Milky Way. When we look in this direction, we peer toward a portion of the galaxy where stars are more sparsely distributed. The luminous spiral arms are less prominent, and the interstellar medium thins out. This provides astronomers with a relatively unobstructed view of the galactic halo in the southern hemisphere, allowing studies of older stars, globular clusters, and distant satellite galaxies. The Sculptor constellation, though modest in brightness, acts as a celestial marker for this direction, guiding astronomers as they map the southern galactic regions. The environment below the plane mirrors much of what we see above it, but with subtle differences. The stellar density remains lower than within the disk, and many of the stars in this region belong to the halo population, ancient stars that orbit the Milky Way in elongated paths rather than circular ones. These stars are relics from the galaxy's formation, survivors of mergers with smaller galaxies over billions of years. Observing below the plane allows astronomers to study these stellar fossils, revealing the evolutionary history of the Milky Way and the processes that shaped its current structure.
Globular clusters are particularly notable in this region. These dense, spherical groups of stars orbit the galactic center in paths that carry them both above and below the plane. Some globular clusters lie preferentially below the plane, moving through Sculptor's direction as they circle the Milky Way. These clusters, containing hundreds of thousands of stars, are among the oldest visible objects in the galaxy, providing crucial insight into the early epochs of star formation. Studying them in the southern galactic hemisphere helps astronomers understand the symmetry and overall architecture of the halo. The interstellar medium also extends below the plane, although it is far less dense than within the disk. Diffuse gas and dust create faint, wispy structures, often influenced by past supernova explosions and stellar winds from the disk above. In some cases, material from the disk has been expelled downward in the form of chimneys or supershells, channels through which hot gas escapes into the halo. These features illustrate that the vertical dimension of the galaxy is dynamic, with matter and energy continually moving between the disk and the halo. Looking below the solar system also provides a vantage point for observing satellite galaxies orbiting the Milky Way. In the direction of Sculptor, astronomers can observe the Sculptor dwarf galaxy, one of the Milky Way's small companion galaxies. These satellites, along with the larger Magellanic Clouds to the south, trace gravitational interactions that shape both the disk and halo. Their orbits, sometimes plunging above and below the plane, highlight the three-dimensional nature of galactic dynamics and provide clues about how galaxies grow by accreting smaller companions. The South Galactic Pole also serves as a key reference in the galactic coordinate system, where latitude is measured as the angle above or below the plane. Negative galactic latitudes point toward this southern direction, allowing astronomers to specify locations relative to the disk with precision. This system is essential for mapping the Milky Way structure in 3 dimensions, describing the positions of stars, gas clouds, and distant galaxies in a standardized framework. While the environment below the plane is less crowded, it is far from empty. Cosmic rays and magnetic fields permeate this region, threading through the tenuous gas and influencing the motion of charged particles. Some of the most energetic phenomena in the galaxy, including remnants of supernova explosions and high-velocity clouds of gas, extend into this vertical space. By observing in multiple wavelengths, from radio waves to X-rays, astronomers can detect these subtle features, providing a fuller understanding of the processes shaping the Milky Way's southern halo. In essence, looking below the solar system means gazing toward the South Galactic Pole, along the axis defined by Sculptor, into a region of the galaxy that is quieter than the dense disk, but rich in structure and history. This direction reveals ancient stars, globular clusters, diffuse interstellar gas, and satellite galaxies, offering a complementary perspective to the northern vertical dimension. Together, above and below, these regions highlight the 3-dimensional nature of the Milky Way, the wave-like path of our solar system, and the vertical layering of the galaxy beyond the familiar spiral arms. By understanding both the northern and southern directions relative to the galactic plane, we gain a true sense of the solar system's position in space. We see that the galaxy is not merely a flat, 2-dimensional disk, it is a layered, dynamic structure, with matter, stars, and energy distributed above and below the plane. These insights set the stage for exploring the stars that inhabit these regions, the halo that surrounds the Milky Way, and the broader cosmic structures that define our place in the universe. Now that we have established the directions of above and below the solar system in a galactic context, we can begin to populate these regions with some familiar neighbors, nearby stars that reside either slightly above or below the Milky Way's plane. While the galaxy spans hundreds of thousands of light-years across, our solar system's immediate stellar neighborhood occupies only a tiny fraction of that volume. Yet even within this small patch of space, the arrangement of stars provides a remarkable 3-dimensional perspective of our position in the Milky Way. Above the galactic plane, in the direction of the North Galactic Pole, we find a variety of stars that occupy the northern vertical hemisphere relative to the solar system's orbit. Among the closest of these is Barnard's star, a red dwarf located about 6 light-years away in the constellation Ophiuchus. Barnard's star is not only notable for its proximity, but also for its high proper motion. It appears to move noticeably against the background stars over human timescales, a reflection of both its speed and closeness. Its position slightly above the galactic plane offers a tangible reference point for astronomers, mapping the local stellar environment along the northern axis. Further out in this above region is Lumen 16, a binary brown dwarf system situated roughly 6.5 light-years away in the constellation Vela when projected along the galactic latitude. Though faint and invisible to the naked eye, Lumen 16 exemplifies the diverse types of stars and substellar objects that populate the halo regions above the disk. These stars, while still close neighbors on a cosmic scale, trace orbits that may carry them further above the plane over time, reflecting the 3-dimensional dynamics of our galactic neighborhood. In the broader northern hemisphere, higher latitude stars also include members of the halo population, ancient stars that occupy inclined orbits around the Milky Way. These stars are typically older, metal-poor, and less luminous than younger disk stars. Observing them above the plane provides insight into the Milky Way's early formation, as many may be relics of smaller galaxies that merged with the Milky Way billions of years ago. Even though they are more distant than nearby red dwarfs, their distribution gives a sense of the vertical thickness of the galaxy and the extended nature of its halo. Turning our gaze below the galactic plane toward the South Galactic Pole, we encounter other familiar neighbors, including Alpha Centauri, our closest star system at 4.37 light-years away. Comprising a triple system, Alpha Centauri A, Alpha Centauri B, and the small red dwarf Proxima Centauri, this system lies slightly below the plane, providing a southern reference point for our immediate stellar neighborhood. Proxima Centauri, the nearest star to the Sun, has been a focal point of study, not only for its proximity, but also for its exoplanet, Proxima Centauri b, which lies within the star's habitable zone. Observing these stars in a vertical context illustrates that even the closest stellar neighbors are not confined to the ecliptic plane of our solar system or the galactic plane, but occupy a three-dimensional volume in space.
Another example of a nearby star slightly below the plane is Wolf 359, a faint red dwarf located approximately 7.8 light-years away in the constellation Leo. Though diminutive and invisible to the naked eye, Wolf 359 contributes to the mass and motion of the solar neighborhood, and its position below the plane underscores the three-dimensional dispersion of stars around the Milky Way's midline. In the southern hemisphere, these stars, together with more distant halo stars and globular clusters, provide a vertical perspective complementary to what we observe above the plane. Nearby multiple star systems, high proper motion stars, and even faint brown dwarfs form a complex lattice around the solar system. Their orbits are influenced not just by the Sun, but also by the Milky Way's gravitational potential, which determines how far above or below the galactic plane they travel over time. By mapping their positions, astronomers can reconstruct the local stellar environment, understand the density of stars in different regions, and predict close encounters that might occur over millions of years. These close stellar neighbors give a tangible sense of spatial orientation. We are not isolated, but embedded in a dynamic three-dimensional neighborhood with stars drifting above, below, and across our path. High-velocity stars, sometimes called halo stars, also pass through the local solar neighborhood along inclined orbits. These stars, often metal-poor and older than typical disk stars, can travel significant distances above or below the plane during their galactic orbits. Observing them provides evidence of past galactic mergers and accretion events, illuminating the history of the Milky Way and its layered structure. Some of these stars, although currently far from the Sun, will eventually swing through our local neighborhood, temporarily altering the stellar density above or below the plane. By examining both northern and southern nearby stars, we begin to see that the local cosmic neighborhood is not a flat disk, but a three-dimensional stellar environment. Stars above the plane, like Barnard's star, and stars below, like Alpha Centauri and Wolf 359, collectively form a volume in space that extends both vertically and horizontally, providing context for the solar system's position relative to the galactic plane. This neighborhood forms a foundation for understanding the vertical distribution of other galactic structures, from gas clouds and interstellar dust to globular clusters and the more distant halo populations. Ultimately, considering nearby stars above and below the plane provides an essential orientation for our position in the Milky Way. These stars act as anchors for mapping our local environment and offer a glimpse into the larger, layered architecture of the galaxy. By tracing their positions, velocities, and orbits, astronomers can study the interplay between local dynamics and the solar system's wave-like motion through the galactic plane, connecting immediate neighbors with broader galactic structures. This vertical perspective brings the vast three-dimensional nature of the Milky Way into sharper focus, helping us appreciate how even our closest stellar companions inhabit the complex space above and below the solar system. Having surveyed the nearby stars above and below the galactic plane, our perspective now widens dramatically as we consider the galactic halo, the vast spherical envelope that surrounds the Milky Way's disk. Unlike the flat, bustling spiral disk, the halo is a diffuse and extended structure that reaches far beyond the visible bounds of the galaxy. It is a component that emphasizes the three-dimensional nature of our galactic home and helps define the larger context of above and below on truly cosmic scales. The galactic halo is composed of several intertwined components: ancient stars, globular clusters, and dark matter. The stars in the halo are typically old, metal-poor, and far less luminous than those in the disk. Many of them formed during the early epochs of the Milky Way's history, long before the spiral arms were fully shaped. These halo stars move in highly elliptical orbits, often taking them far above or below the galactic plane, in contrast to the nearly circular orbits of most disk stars. Their presence serves as a living fossil record of the galaxy's early formation processes, providing clues about mergers with smaller galaxies and the accretion of material over billions of years. Interspersed within the halo are globular clusters, dense spherical assemblies of stars numbering in the hundreds of thousands. These clusters orbit the galactic center in paths that carry them through the halo, often traveling above and below the plane. They are among the oldest objects in the galaxy, with ages approaching 12 to 13 billion years, offering a glimpse into the earliest star formation episodes in the universe. Their orbits are not confined to the disk, so they trace out the halo's three-dimensional shape, forming a glittering halo of stellar light around the Milky Way's luminous spiral. Famous examples include M13 in Hercules and Omega Centauri, the largest globular cluster in our galaxy, whose stars move along highly inclined orbits that bring them far from the galactic midplane. Beyond visible stars and clusters, the halo is dominated by dark matter, the mysterious invisible substance that exerts gravitational influence without emitting light. Dark matter forms a roughly spherical distribution that envelops the Milky Way, extending far beyond the luminous disk. Its gravitational pull governs the orbits of stars, clusters, and even satellite galaxies, effectively holding the galaxy together and dictating the motion of the solar system as it oscillates above and below the disk. Although we cannot see dark matter directly, its presence is inferred through observations of rotational velocities and orbital dynamics throughout the galaxy. The halo is vast. While the Milky Way's disk spans roughly 100,000 light-years, the halo may extend several 100,000 light-years in radius, gradually thinning as one moves away from the central disk. Within this enormous volume, the density of stars is extremely low compared to the disk, creating a more open, sparse environment. Yet it is far from empty. Ancient stars, clusters, and diffuse gas thread the halo, providing both a historical record and a gravitational scaffold for the Milky Way. Within the halo, structures such as stellar streams, remnants of dwarf galaxies torn apart by tidal forces, snake across the sky, sometimes intersecting the solar neighborhood. These streams, like the Sagittarius stream, offer a dramatic demonstration of the halo's dynamic nature, revealing how the galaxy has grown by accreting smaller companions over billions of years. Observing these streams in 3 dimensions highlights the halo's complex geometry and shows that above and below the galactic plane are meaningful not only locally but across the vast reaches of the Milky Way.
The halo also serves as a boundary for the galaxy's gravitational influence. Satellite galaxies, such as the Large and Small Magellanic Clouds, orbit within this extended halo, moving along trajectories that are often inclined to the disk. Their motion, shaped by the halo's mass distribution, demonstrates that the galactic halo is not merely a passive envelope, but an active player in the evolution and dynamics of the Milky Way. Even our own solar system, though deep within the disk, is affected by the halo's gravitational pull as it oscillates above and below the plane. Gas in the halo, while extremely diffuse, is also present and contributes to the galaxy's evolution. Observations of high-velocity clouds, streams of hydrogen moving rapidly relative to the disk, show that the halo contains both hot and cold components. Some of this gas is falling inward, potentially fueling future star formation in the disk, while other material is being expelled outward, lifted by supernovae and stellar winds from the disk. The halo thus acts as a dynamic reservoir, connecting the energetic activity of the disk with the outermost reaches of the galaxy. In essence, the galactic halo frames the Milky Way as a 3-dimensional structure, rather than a mere flat spiral. The disk, where most of the stars and star formation reside, sits at the center of the spherical halo, while the halo itself extends far above and below, populated by ancient stars, globular clusters, and the unseen dark matter that dominates the galaxy's mass.
Understanding the halo provides context for the vertical motions of stars, the paths of globular clusters, and even the oscillations of our solar system as it moves through the galaxy. Looking outward from the solar system, the halo reminds us that what lies above or below the galactic plane is more than empty space. It is a layered, dynamic environment that preserves the galaxy's history, supports its present, and shapes its future. The stars and clusters of the halo illuminate the past, dark matter governs the motions of everything within it, and streams of gas and disrupted satellites illustrate the ongoing evolution of the Milky Way. Together, these components make the galactic halo a critical three-dimensional structure, giving depth and perspective to the notion of up and down in our cosmic neighborhood. By considering the halo alongside the disk, we begin to appreciate that the solar system is nestled within a layered and dynamic galaxy, surrounded on all sides by a complex mixture of stars, gas, clusters, and dark matter. This vertical structure, stretching both above and below the plane, sets the stage for examining the globular clusters in more detail, which orbit the Milky Way from above and below, forming part of this glittering halo. With the galactic halo as our backdrop, we now focus on one of its most visually striking and scientifically significant components, globular clusters. These densely packed spherical collections of stars are among the oldest known objects in the galaxy, and their orbits carry them above and below the Milky Way's disk, creating a glittering halo of ancient stars that encircle the galaxy. Understanding globular clusters provides both a window into the early history of the Milky Way and a way to appreciate the three-dimensional complexity of our galaxy. Globular clusters typically contain hundreds of thousands to millions of stars, bound tightly together by gravity. They are remarkably compact. While a typical open cluster in the disk might span a few light years, a globular cluster can be 100 light years in diameter, packed with stars from its dense core to the sparsely populated outer regions. The stars within globular clusters are almost universally old and metal-poor, meaning they formed before heavier elements like iron and carbon were abundant in the universe. This age places them among the earliest products of star formation in the galaxy, often 12 to 13 billion years old, just slightly younger than the Milky Way itself. The orbits of globular clusters distinguish them from the stars in the disk. Rather than moving in nearly circular paths confined to the galactic plane, globular clusters follow elliptical orbits that can be highly inclined. Some plunge close to the galactic center before swinging far out into the halo, while others remain in broader, more circular orbits but still traverse significant distances above and below the disk. This vertical motion, combined with their radial excursions, ensures that globular clusters populate the halo in a roughly spherical distribution, surrounding the disk with a dense and luminous cloud of ancient stars. From our perspective on Earth, globular clusters appear as faint, concentrated patches of light, often best viewed through telescopes. Iconic examples above the galactic plane include M13 in Hercules, visible in the northern sky, and M3 and Cain's Venatici, both of which reside far above the disk. In the southern hemisphere, below the galactic plane, clusters such as Omega Centauri and 47 Tuc dominate the view, offering spectacular evidence of the halo's richness. Their distribution demonstrates that the halo is not empty, but filled with compact stellar systems moving in 3 dimensions around the galaxy. The formation of globular clusters remains an area of active research, but they are generally thought to have formed in the early epochs of the Milky Way or in smaller proto-galaxies that later merged with the Milky Way. As relics of these formative periods, globular clusters carry chemical signatures and stellar populations that provide insight into conditions in the early universe. Observing their orbits above and below the galactic plane allows astronomers to reconstruct the Milky Way's assembly history, tracing back collisions, accretions, and gravitational interactions that help shape the halo we see today. In addition to stars, globular clusters contain low-mass remnants, such as white dwarfs and neutron stars, which have persisted over billions of years.
Their tightly packed nature creates fascinating dynamical interactions. Stars can pass extremely close to one another, occasionally leading to gravitational slingshots, binary formation, or even collisions. Some clusters also harbor intermediate mass black holes at their centers, hinting at the complexity and gravitational intensity of these ancient stellar cities.
The spatial relationship of globular clusters to the Milky Way's disk is key to understanding their role in galactic structure. Their vertical orbits mean they often pass through or near the plane during their motion, but they spend much of their time far above or below it. This movement creates a three-dimensional halo of stars that extends thousands of light years from the galactic midplane, enveloping the disk like a luminous cloud. The visual effect is a spherical shell of light surrounding the flat spiral, emphasizing the layered architecture of the galaxy, a dense, active disk encircled by a halo populated with globular clusters and ancient stars. Studying globular clusters also helps refine our understanding of the Milky Way's mass distribution. Because their orbits are determined by gravity, astronomers can track their positions and velocities to infer the presence of dark matter, which dominates the halo and influences the motion of all halo objects. Observations of clusters above and below the plane, combined with measurements of satellite galaxies and high-velocity stars, provide a three-dimensional map of the galaxy's gravitational potential. In essence, globular clusters act as tracers, revealing the invisible scaffolding of mass that holds the Milky Way together. Globular clusters also illustrate the continuity between local and galactic scales. While individual stars in our solar neighborhood define the immediate vertical structure around the Sun, globular clusters extend that vertical view to thousands of light years above and below the disk. This expansion of scale shows how the galaxy is layered. The solar system oscillates gently within a few tens of light years of the plane. Local stars span hundreds of light years, and globular clusters populate the halo for tens of thousands of light years, all tracing the three-dimensional structure of the Milky Way. Finally, the visual beauty of globular clusters above and below the plane is matched by their scientific significance. Each cluster is a snapshot of the early Milky Way, a time capsule containing clues to stellar evolution, chemical enrichment, and galactic formation. Their orbits, extending high above and deep below the disk, remind us that the galaxy is not a flat spiral, but a complex three-dimensional structure where stars, gas, and dark matter interact in a dynamic cosmic dance. Observing these clusters in the northern and southern halos provides a tangible framework for understanding the vertical structure of the Milky Way and appreciating the vast spaces our solar system inhabits within it. In summary, globular clusters orbit the Milky Way's center along paths that take them above and below the galactic disk, forming a luminous three-dimensional halo of ancient stars. They serve as tracers of the galaxy's gravitational potential, relics of its formative history, and markers of the vertical extent of the Milky Way. Their presence above and below the disk illuminates the layered spherical structure of the halo and reinforces the concept of three-dimensional galactic space, helping us contextualize the solar system's position within this immense cosmic architecture. Building on the halo and globular clusters, we now turn our attention to the interstellar medium, ISM, the vast but tenuous material that fills the spaces between stars. Though it is far less dense than the stars themselves, the ISM is a fundamental component of the galaxy, providing the raw material for star formation, influencing galactic dynamics, and extending both above and below the galactic plane. Understanding its distribution and properties is essential for appreciating the three-dimensional structure of the Milky Way and the environments that surround our solar system. The interstellar medium is composed primarily of gas, roughly 99% of its mass, and dust, which makes up the remaining 1%. The gas is mostly hydrogen, the universe's most abundant element, with smaller amounts of helium, carbon, oxygen, nitrogen, and trace metals. Dust grains are tiny solid particles composed of silicates, carbon, and ices, which absorb and scatter light. Despite its low density, often only a few atoms per cubic centimeter,
The ISM plays an outsized role in the galaxy. It governs how light propagates, serves as the birthplace of new stars, and provides the medium through which shockwaves, cosmic rays, and magnetic fields travel. Within the galactic plane, the ISM is densest. This is where the spiral arms lie, rich with molecular clouds, star-forming regions, and nebula. Molecular clouds such as the Orion Nebula are dense pockets within the ISM where gravity overcomes internal pressure, leading to the collapse of gas and the birth of new stars. The plane's higher density also means that extinction, the dimming of starlight by dust, is most pronounced here. This concentration of gas and dust contributes to the visible structure of the galaxy, highlighting spiral arms and dense dark clusters. Moving above and below the galactic plane, the ISM becomes far more diffuse. In the halo, hydrogen is primarily in atomic or ionized form, with densities many orders of magnitude lower than in the disk. Here, the medium exists as a thin, extended layer, sometimes forming high-velocity clouds that travel through the halo at speeds exceeding 100 kilometers per second. These clouds may originate from supernova-driven outflows in the disk, or be remnants of infalling material from satellite galaxies. Despite its low density, this gas contributes to the overall mass of the halo and participates in galactic recycling processes, transporting material between the disk and halo over millions of years. Dust is also present above and below the plane, though in smaller quantities. Observations of distant stars and galaxies show that even at high galactic latitudes, dust scatters light, creating faint extinction features known as cirrus clouds. These high-latitude dust structures are often filamentary and patchy, revealing that the ISM is far from uniform. In combination with gas, these dust structures interact with cosmic rays and magnetic fields, shaping the dynamics and chemistry of the surrounding medium.
The ISM is dynamic, not static. Supernova explosions in the disk generate shock waves that propagate into the halo, compressing gas, forming bubbles, and pushing material upward and downward relative to the plane. These expanding shells create chimneys through which hot gas and energetic particles escape into the halo, forming a feedback loop between star formation in the disk and the extended ISM above and below. Over millions of years, these processes stir the interstellar medium, maintaining turbulence, mixing chemical elements, and influencing the orbits of stars and star clusters that pass through these regions. Magnetic fields thread the ISM both in the disk and the halo, guiding the motion of charged particles and influencing gas dynamics. Cosmic rays, high-energy particles traveling at near light speeds, propagate through the ISM and halo, interacting with gas and dust, contributing to heating and generating faint radio emissions observable from Earth. This interplay of magnetic fields, cosmic rays, and the interstellar medium demonstrates that the space above and below the plane, while less populated by stars, is far from empty or inert. The vertical extent of the ISM also contributes to the solar system's environment. Our solar system resides in a region known as the local bubble, a low-density cavity within the ISM created by ancient supernova explosions. This bubble, roughly 300 light-years across, provides a protective, relatively low-density environment around the Sun, reducing the flux of cosmic rays compared to denser regions of the disk. Yet surrounding the local bubble are denser clouds, some lying above and below the plane, which act as reservoirs of gas and dust and participate in the ongoing circulation of matter through the galaxy. Studying the ISM above and below the plane is crucial for understanding galactic ecology. The disk's dense molecular clouds form new stars, while the halo's tenuous gas participates in recycling and mass transport. By observing the ISM in multiple wavelengths, from radio and infrared, which trace cold gas and dust, to ultraviolet and X-ray, which reveal hot ionized gas, astronomers can construct a three-dimensional map of the material that threads through the galaxy, enveloping the solar system and influencing its galactic journey. In summary, the interstellar medium is a pervasive, dynamic substance composed of gas and dust stretching across the Milky Way's disk and extending far above and below it. While densest in the midplane, it thins progressively into the halo, where high-velocity clouds, magnetic fields, and diffuse gas
create a less crowded but still active environment. The ISM links the stars, clusters, and dark matter of the galaxy, shaping its structure and evolution. By examining this medium in the vertical dimension, we gain insight into the processes that govern star formation, chemical enrichment, and the circulation of matter across the galaxy, framing the solar system within a dynamic, three-dimensional galactic ecosystem. Having explored the interstellar medium that fills the spaces between stars, we now turn to a more invisible but equally pervasive component of the Milky Way, the galactic magnetic field. Though intangible to human senses, these magnetic fields thread through the galaxy, arching above and below the disk, shaping the motion of charged particles, guiding gas flows, and subtly influencing the large-scale structure of the interstellar medium. Understanding the galactic magnetic field is essential to grasping how the Milky Way functions as a dynamic three-dimensional system and how the solar system interacts with its broader cosmic environment. The galactic magnetic field is primarily generated by a dynamo mechanism, arising from the motion of conductive plasma in the galaxy. As ionized gas and plasma rotate and move within the Milky Way's disk, their motions create and sustain large-scale magnetic fields. These fields are not uniform. They vary in strength and orientation across the galaxy. In the disk, the field typically follows the spiral arms, aligned along the curvature of the stellar pattern. However, the field is not confined to the flat disk. Observations reveal that it arches vertically above and below the plane, extending into the halo and influencing the behavior of gas, dust, and cosmic rays in these regions. The field strength of the galactic magnetic field is relatively modest by human standards, averaging a few microgauss, about 1,000,000 times weaker than a refrigerator magnet. Yet over the vast distances of the Milky Way, even this faint force has a profound effect. Charged particles, including the high-energy cosmic rays that permeate the galaxy, spiral along magnetic field lines rather than moving in straight trajectories. This deflection protects the disk and the solar system from a direct, unmoderated influx of cosmic rays, while also contributing to the confinement of cosmic rays over millions of years. In this way, the magnetic field helps regulate the radiation environment across both the disk and the halo. Above and below the galactic plane, the magnetic field interacts with the tenuous interstellar medium in the halo. Hot ionized gas, ejected from the disk by supernova explosions and stellar winds, follows the contours of the magnetic field, forming filamentary structures, loops, and bubbles that rise into the halo. These magnetic funnels guide gas flows, preventing some material from freely dispersing into intergalactic space, while channeling other material along predictable paths. Observations in radio and X-ray wavelengths reveal these structures, showing arcs and plumes that extend thousands of light years above and below the disk. The magnetic field also affects star formation. Within dense molecular clouds in the disk, magnetic forces provide support against gravitational collapse, influencing the rate at which new stars form. While the field is weaker in the halo, its influence on the dynamics of diffuse gas cannot be ignored. The alignment of magnetic fields can stabilize structures, guide the motion of high-velocity clouds, and even affect the accretion of material from the halo back into the disk. In this sense, the magnetic field functions as both a structural and regulatory element in the galaxy, linking vertical and horizontal dynamics across tens of thousands of light years. Mapping the galactic magnetic field is a complex task. Astronomers use several indirect techniques, including the polarization of starlight, the Faraday rotation of radio waves, and synchrotron emission from electrons spiraling along field lines. These methods reveal that the field is not static. It exhibits turbulence on smaller scales, superimposed on a more coherent large-scale pattern. This turbulent component contributes to the random motion of gas in the disk and the halo, and plays a role in the mixing of chemical elements and the propagation of energy throughout the galaxy. The field's vertical component, extending above and below the plane, emphasizes the three-dimensional nature of the Milky Way. It is not confined to the plane of the disk, but arches into the halo, connecting the dense star-forming regions of the disk with the sparse extended regions above and below. These vertical field lines influence the paths of globular clusters, high-velocity stars, and cosmic rays moving through the halo, creating a subtle but pervasive network that shapes galactic dynamics. Without these fields, the distribution of gas and charged particles in the halo would be far more chaotic, and the structure of the interstellar medium would be markedly different.
For the solar system, the galactic magnetic field has both indirect and direct effects. Cosmic rays entering our local environment are partially deflected by the field, influencing radiation levels at Earth and in near space. The magnetic field also interacts with the heliosphere, the protective bubble generated by the solar wind, modulating the flux of charged particles that reach our planetary system. In this way, the galaxy's magnetic field extends its influence even into the localized region around the Sun, connecting cosmic-scale processes with our immediate environment. In summary, the galactic magnetic field threads through the Milky Way like an invisible skeleton, extending above and below the disk and shaping the behavior of gas, cosmic rays, and other charged particles. It creates structure in the interstellar medium, guides matter moving between the disk and halo, and regulates the environment for star formation and particle propagation. By arching into the halo, it emphasizes that the galaxy is a three-dimensional, dynamic system, with vertical connections linking the plane, the halo, and the solar system itself. Understanding this magnetic architecture deepens our comprehension of what lies above and below the solar system, revealing a layer of complexity that is invisible to the eye but essential to the galaxy's functioning. Continuing our exploration of the Milky Way structure, we now turn to a subtle but important feature, the galactic warp. While we often depict the Milky Way as a flat, graceful spiral when viewed from above or below, the reality is more complex. The disk of our galaxy is not perfectly planar. Instead, it exhibits a gentle warp, a bending of the stellar and gaseous disk that causes what we consider above and below to vary depending on where we look. This warp has significant implications for understanding the vertical structure of the galaxy, the distribution of stars and gas, and even the motion of the solar system relative to the galactic plane. The galactic warp is most apparent in the distribution of neutral hydrogen gas, H1, which extends far beyond the bright stellar disk. Observations in radio wavelengths reveal that the outer regions of the Milky Way are not aligned with the inner disk. Instead, the gas layers curve upward on one side of the galaxy and downward on the opposite side, creating a subtle S-shaped or warped pattern. This means that a star located in the outer disk may be positioned several thousand light-years above or below the plane defined by the inner galaxy. In effect, the midplane itself is not uniform. It undulates gently as one moves radially outward from the galactic center. The warp affects both stars and gas, although it is more pronounced in the extended gaseous disk. Stars in the outer disk follow the warped contours, resulting in vertical displacements of hundreds of light-years above or below the plane observed in the inner galaxy. This phenomenon has been mapped through surveys of distant stars and star clusters, confirming that the warp is a large-scale feature of the Milky Way. In combination with the solar system's oscillation above and below the galactic plane, the warp introduces an additional layer of complexity to our understanding of up and down, emphasizing that vertical orientation is not absolute, but depends on your location within the galaxy. The causes of the warp are still an active area of research, but several mechanisms are believed to contribute. Gravitational interactions with satellite galaxies, such as the Large and Small Magellanic Clouds, exert tidal forces that distort the outer disk. The dark matter halo may also play a role, as misalignments between the disk and halo's mass distribution can induce bending in the stellar and gaseous layers. Additionally, infalling gas from the intergalactic medium may exert torque on the outer disk, further contributing to its warped shape. These combined effects result in a disk that is neither perfectly flat nor static, but gently flexing and bending over cosmic timescales. For the solar system, the warp has subtle but measurable implications. While we orbit within the inner disk, where the warp is minimal, the outer edges of the galaxy bend above and below the midplane. This means that objects far from the galactic center, whether stars, gas clouds, or globular clusters, may reside at vertical positions that do not align neatly with the plane defined by the Sun's orbit.
Observations of distant stellar populations must account for the warp to accurately determine their positions and velocities. Similarly, when mapping the distribution of gas, the warp explains why neutral hydrogen and molecular clouds in the outer galaxy appear displaced relative to the inner disk. The warp also has implications for the vertical structure of the interstellar medium. As a disk bends, gas in the outer regions follow the curvature, creating variations in density above and below the nominal midplane. High-latitude clouds in the outer disk may thus be associated with the warp structure, influencing how matter circulates between the disk and halo. Supernova, stellar winds, and magnetic fields in these regions interact with the warped gas, producing subtle asymmetries in the ISM structure and dynamics. In terms of perspective, the warp reinforces the idea that above and below are relative concepts. Near the solar system, above is towards the north galactic pole, and below towards the south galactic pole. Yet, in the warped outer disk, these directions may intersect regions that are hundreds or even thousands of light years displaced from the plane defined by our local orbit. This three-dimensional undulation challenges simple notions of a flat galaxy and highlights the need to consider both local and global perspectives when exploring the Milky Way's vertical structure.
Observationally, the warp has been confirmed by multiple surveys, including radio observations of HI gas, infrared mapping of stars, and studies of distant molecular clouds. The warp appears to be more pronounced in the outermost regions, roughly beyond 15 to 20 kiloparsecs from the galactic center, whereas the inner disk remains relatively flat. This differential bending creates a complex, gently twisting structure that must be accounted for in models of galactic dynamics, star formation, and the behavior of the interstellar medium. Ultimately, the galactic warp reminds us that the Milky Way is a living, dynamic system, not a static, flat disk. Its undulations, combined with the vertical oscillations of the solar system and the layered halo of stars and globular clusters, demonstrate the three-dimensional complexity of the galaxy. Above and below the plane, the warp alters the local reference frame, affecting the positions of stars, gas, and clusters, and influencing how astronomers interpret vertical structure on both local and cosmic scales. Understanding this feature provides crucial context for subsequent discussions about the motion of the solar system, the distribution of nearby and distant stars, and the broader environment of the Milky Way's halo. In summary, the galactic warp is a gentle bending of the Milky Way's disk that introduces variation in what we define as above and below. While the inner disk remains relatively flat, the outer regions curve upward and downward, creating a dynamic, three-dimensional structure. This warp, combined with the solar system's oscillations and the vertical distribution of stars and clusters, reinforces the complex, layered nature of the galaxy and highlights that vertical orientation in space is relative, dependent on one's position within this undulating spiral. Having examined the Milky Way's warped disk and vertical structure, it's essential to consider the motion of our solar system within this dynamic environment. The Sun is not stationary. It orbits the galactic center at an astonishing speed of approximately 220 kilometers per second, completing one full revolution roughly every 225-250 million years, a period known as a galactic year. This orbit is nearly circular, but not perfectly so, and it is accompanied by a subtle up and down oscillation as the solar system moves through the galactic plane, creating a wave-like trajectory that carries us above and below the midplane approximately every 30 million years. Understanding this motion is crucial for grasping how the solar system interacts with the galactic disk, halo, and surrounding structures. The solar system's orbit is governed primarily by the gravitational pull of the galaxy's mass, including stars, gas, dust, and the elusive dark matter halo. While most stars in the disk orbit in roughly circular paths, the gravitational influence of spiral arms, the central bulge, and perturbations from nearby stars and satellite galaxies introduces slight variations in speed and direction. Over millions of years, these perturbations caused the solar system to oscillate vertically relative to the galactic plane, moving up into the halo before descending back through the disk. This motion produces a three-dimensional path that is not confined to the flat plane of the galaxy,
but instead resembles a gentle sine wave traced through the spiral disk. The vertical oscillation above and below the plane is particularly interesting. As the solar system rises, it moves into regions of lower stellar density and thinner interstellar medium, somewhat akin to the halo environment. Conversely, as it passes through the midplane, the density of stars, gas, and dust is at its maximum. These oscillations influence the solar system's exposure to cosmic radiation, encounters with interstellar clouds, and potential gravitational perturbations from nearby stars. Over the course of hundreds of millions of years, this vertical movement may have had subtle effects on the solar system's environment, including the flux of comets entering the inner system from the Oort cloud, which lies far above and below the plane. The orbit of the Sun is also influenced by the Milky Way spiral arms, regions of higher density where star formation is active. As the solar system moves around the galaxy, it periodically passes through these arms, which can perturb the orbits of comets and stars in the vicinity and alter the local interstellar environment. However, the vertical oscillation ensures that the Sun is not always in the dense plane. Much of its trajectory carries it into less crowded regions above and below the disk, providing a measure of protection from direct interactions with the densest star-forming regions. The amplitude of the solar system's vertical motion is estimated to be about 70 to 100 light-years above or below the midplane. While this is small compared to the total thickness of the galaxy or the extent of the halo, it is significant in the context of the local interstellar environment. During these oscillations, the solar system alternately traverses regions of varying interstellar density, magnetic field strength, and cosmic ray flux, all of which have implications for the heliosphere, the protective bubble created by the solar wind, and for the broader galactic context in which Earth and other planets exist. This motion also provides a dynamic perspective on the concept of above and below. From a local perspective, above is toward the North Galactic Pole, and below toward the South Galactic Pole. However, as the solar system oscillates, it moves through these directions, rising slightly above and then descending slightly below the midplane. Over tens of millions of years, this gentle vertical motion ensures that the solar system experiences the full three-dimensional structure of the disk and nearby halo, interacting with interstellar clouds, magnetic fields, and local stellar populations along the way.
The speed of 220 kilometers per second is mind-boggling when considered on human scales. In just one Earth year, the solar system travels roughly 4.4 billion kilometers, or nearly 30 times the distance from the Earth to the Sun. Over the course of a galactic year, we traverse billions of light-years of distance relative to the galaxy, all while oscillating vertically through the galactic disk. This constant motion emphasizes that the solar system is not a fixed point in space, but a traveler through a three-dimensional dynamic galaxy intimately connected to the Milky Way's disk, halo, and extended structures. Observations of the Sun's motion are facilitated by measuring the proper motion of nearby stars and the Doppler shifts of objects at various distances. By tracking these movements, astronomers reconstruct not only the Sun's orbit, but also the distribution of mass throughout the galaxy, including the dark matter halo that exerts a dominant gravitational influence. This allows the calculation of both the horizontal orbital speed and the vertical oscillation, revealing a dynamic environment in which the solar system navigates both the flat disk and the surrounding halo. In summary, the solar system orbits the center of the Milky Way at roughly 220 kilometers per second, completing a full revolution every 225 to 250 million years. Simultaneously, it oscillates above and below the galactic plane approximately every 30 million years, moving through regions of varying stellar density, interstellar medium, and magnetic influence. This wave-like motion emphasizes the three-dimensional nature of the galaxy, illustrating that our solar system is not fixed in a two-dimensional disk, but is instead embedded within a dynamic, vertically extended, and intricately structured galaxy. Having traced the solar system's journey through the Milky Way, from the warped disk to the oscillating motion above and below the galactic plane, it's time to zoom out and consider what lies beyond the Milky Way itself. The galaxy we inhabit is vast, but it is merely one of billions in the universe. Above and below its disk stretches intergalactic space, an immense and mostly invisible realm that serves as the cosmic environment for our galaxy, influencing its motion, evolution, and the distribution of matter on the largest scales. Understanding this intergalactic context expands our perspective of above and below,
showing that these concepts extend far beyond our immediate stellar neighborhood. Intergalactic space is dominated by dark matter, the invisible substance that makes up roughly 85% of the matter in the universe. This dark matter forms cosmic filaments, vast structures that stretch across millions of light years, connecting galaxies like strands in a web. Our Milky Way, along with its neighboring galaxies in the local group, resides within one of these filaments. Above and below the galactic plane, on scales vastly larger than the halo or disk, these filaments provide the gravitational scaffolding for the distribution of galaxies, influencing their motion, interactions, and eventual mergers. In addition to dark matter, intergalactic space contains extremely diffuse gas, primarily hydrogen and helium left over from the Big Bang. This intergalactic medium, IgM, is often highly ionized and stretches between galaxies at densities of just a few atoms per cubic meter. Although nearly a vacuum by earthly standards, the IgM plays a crucial role in galactic evolution. Gas from the IgM can be accreted onto galaxies, fueling star formation, while outflows from galaxies, driven by supernovae and active galactic nuclei, enrich intergalactic space with heavier elements. In this way, the space above and below the Milky Way's disk ultimately merges with the larger cosmic web, linking our galaxy to a universe of matter and energy on incomprehensible scales. Beyond the Milky Way's halo, we also encounter neighboring galaxies. The Milky Way is part of the local group, a collection of more than 50 galaxies bound together by gravity. Key members include the Andromeda Galaxy, M31, the Triangulum Galaxy, M33, and numerous dwarf satellites, such as the Sagittarius Dwarf and Sculpture Dwarf. These galaxies occupy positions above, below, and around the Milky Way in 3 dimensions, orbiting the shared center of mass of the local group. Their presence highlights that the universe is not empty. Even in the vast intergalactic regions above and below the Milky Way, matter is organized into discrete galaxies and clusters. The distances involved are staggering. While the Milky Way's halo might extend a few 100,000 light-years from the disk, the nearest large galaxy, Andromeda, lies roughly 2.5 million light-years away. The space in between, though sparse, contains the IgM, dark matter filaments, and the occasional satellite galaxy. This intergalactic environment shapes the Milky Way's trajectory through space, influencing its future collision course with Andromeda, an event expected in about 4 billion years, and the distribution of tidal debris that will eventually populate the expanded halo of the merged galaxy. On even larger scales, above and below the Milky Way lie the cosmic voids and superclusters. Voids are enormous regions of low galaxy density, essentially vast cosmic cavities, while superclusters are dense, gravitationally bound groupings of galaxy clusters. The Milky Way resides in a filament known as the Laniakea supercluster, a gravitationally coherent structure containing roughly 100,000 galaxies. The orientation of this filament means that above and below the Milky Way, in an intergalactic sense, is defined by the geometry of these immense cosmic structures. These scales dwarf the Milky Way itself, yet they establish the gravitational and material context in which our galaxy exists. Intergalactic space is not empty of light either. Observations in the ultraviolet, X-ray, and radio bands reveal faint emission from ionized gas and filaments, while gravitational lensing traces dark matter concentrations invisible to traditional telescopes. Even at these enormous distances, the structures above and below the Milky Way interact subtly with our galaxy, guiding its motion through the local group and eventually toward the Virgo cluster, the nearest massive galaxy cluster about 50 million light-years away. Over billions of years, these interactions will continue to shape the Milky Way's evolution. Zooming out, we see that the Milky Way is a small island of stars in a vast cosmic ocean. The above and below directions that define the vertical structure of our solar system and galaxy scale outward into the universe, connecting our galaxy's halo to intergalactic filaments, neighboring galaxies, and the large-scale cosmic web. This perspective reinforces the idea that vertical orientation is relative, dependent on the scale being considered. While the north and south galactic poles provide local references, on intergalactic scales, up and down are defined by the distribution of matter across millions of light-years. In essence, looking beyond the Milky Way transforms our understanding of spatial orientation. Above and below the galaxy lie intergalactic space, a mixture of dark matter, diffuse gas, and distant galaxies interconnected in the cosmic web. These structures set the gravitational landscape that governs the Milky Way's motion, influence the accretion of material onto our galaxy, and connect us to a universe of extraordinary scale and complexity. In this sense, exploring what lies above and below the Milky Way is not just an exercise in local galactic cartography, it is a journey into the architecture of the universe itself. As we pull back from the vast intergalactic scales, it's time to refocus on the solar system's immediate environment and the unique region it occupies, the local bubble. This is a fascinating feature of the interstellar medium, a cavity of hot, low-density gas carved into the Milky Way's disk by ancient supernova explosions. Stretching roughly 300 light-years across, the local bubble envelops the Sun and provides a distinctive perspective on what lies above and below our solar system on relatively local scales, bridging the immediate neighborhood with the broader galactic environment.
The local bubble is primarily filled with ionized gas at temperatures of roughly 1 million Kelvin, far hotter than the surrounding interstellar medium. Despite its high temperature, the density is extremely low, with only about 0.05 atoms per cubic centimeter, a fraction of the density found in the average galactic disk. This combination of high temperature and low density makes the bubble almost invisible in optical light, but it can be detected in X-ray and ultraviolet emissions, as well as through absorption studies of background stars. It is surrounded by denser interstellar clouds, often referred to as the local fluff or interstellar clouds, which mark the boundary between the bubble and the more typical ISM of the Milky Way. The formation of the local bubble is believed to be the result of multiple supernovae that exploded in the solar neighborhood over the last 10 to 20 million years. These catastrophic events expelled gas and energy, clearing out a cavity and heating the remaining material to extreme temperatures. The combined effect of these explosions created an elongated, irregularly shaped region, with its axis roughly aligned with the plane of the Milky Way. While the Sun is not at the exact center of the bubble, it currently resides within this hot cavity, moving slowly through its relatively empty interior. The local bubble has important implications for the solar system's interstellar environment. Because the density of gas is so low, cosmic rays and interstellar particles encounter less resistance, potentially affecting the heliosphere, the protective bubble generated by the solar wind. The low density also means that dust and gas clouds above and below the plane of the Milky Way are more sparsely distributed locally, which influences observations of nearby stars and the structure of the interstellar medium. In essence, the local bubble acts as a kind of cosmic void surrounding the solar system, providing a unique vantage point on the dynamics of the surrounding ISM. Above and below the solar system, the boundaries of the local bubble are defined by the surrounding denser interstellar clouds, including the gold belt of young stars and molecular clouds. These clouds are irregularly distributed, with some regions closer to the Sun than others, creating a patchwork of dense and rarefied regions. The interaction between the hot bubble gas and the cooler surrounding clouds generates shock fronts and ionization fronts, which in turn influence the chemistry and dynamics of the local interstellar medium. This interaction is a vivid demonstration of the galaxy's layered structure, where local phenomena, like supernovae, create features that extend above and below the disk on scales of hundreds of light years. The local bubble is not isolated. It merges with other nearby cavities and bubbles created by stellar activity, forming a network of interconnected low-density regions in the solar neighborhood. This network has been mapped using absorption lines in the spectra of nearby stars and X-ray emission from hot gas, revealing a complex three-dimensional structure of voids and walls. Above the plane of the Milky Way, the local bubble extends into regions of low-density gas that connect to the larger halo, while below the plane it interacts with similar cavities, highlighting the vertical complexity of our local galactic environment. Studying the local bubble also provides insight into the history of star formation near the Sun. The supernovae that created it were likely members of past generations of massive stars, whose death throes shaped the interstellar medium.
These explosions not only carved out the bubble, but also enriched the surrounding ISM with heavier elements, contributing to the material from which new stars and planetary systems, including our own, would eventually form. The local bubble therefore represents both a relic of past stellar activity and a current frame for the solar system's position within the galaxy. In terms of perspective, the local bubble emphasizes that above and below are highly scale-dependent. Locally, above and below the solar system can be defined relative to the midplane of the local bubble and its surrounding interstellar clouds. On a galactic scale, these directions are aligned with the north and south galactic poles. The bubble provides a microcosm of the Milky Way's larger structure, a layered system in which low-density cavities and dense clouds coexist, and the vertical distribution of gas and stars varies depending on location. In summary, the local bubble is a hot, low-density cavity surrounding the solar system, formed by ancient supernova and stretching roughly 300 light-years across. Its interior is extremely tenuous compared to the average interstellar medium, while above and below lie denser clouds that define its boundaries. This region not only shapes the local cosmic environment, but also illustrates the three-dimensional complexity of the Milky Way on local scales. By understanding the local bubble, we gain insight into the solar system's immediate surroundings, the vertical structure of nearby interstellar material, and the dynamic processes that continue to shape our galaxy. Continuing our journey from the solar system's local environment, it is essential to understand the framework astronomers use to define directions in our galaxy, particularly the notions of up and down. In space, there is no absolute vertical. These directions are human constructs based on reference points within the Milky Way. To provide a consistent system, astronomers rely on galactic coordinates, which are anchored to the galactic center and the galactic poles. This coordinate system allows us to define positions, motion, and orientation within the galaxy, and it underpins all discussions of what lies above or below the solar system. At the heart of the Milky Way lies the galactic center, located approximately 27,700 light-years from the Sun in the direction of the constellation Sagittarius. This central region is dense with stars, gas, dust, and a supermassive black hole known as Sagittarius A, which has a mass of about 4 million solar masses. The galactic center provides a natural reference for the plane of the Milky Way as the overall disk of stars and gas rotates around this point. By aligning our coordinate system with the galactic center, astronomers can map the positions of stars, star clusters, and interstellar structures in a consistent three-dimensional framework. Perpendicular to the galactic plane are the galactic poles. The North Galactic Pole, or NGP, points roughly toward the constellation Coma Berenices, while the South Galactic Pole, or SGP, lies in the direction of Sculptor. These poles are analogous to the Earth's north and south poles, but are oriented relative to the plane of the Milky Way rather than Earth's rotation axis. The NGP defines what is above the galactic plane, and the SGP defines what is below. Using these poles, astronomers can assign galactic latitude, which measures angular distance above or below the plane, and galactic longitude, which measures the angular position along the plane relative to the galactic center. Galactic coordinates are crucial because they provide a consistent frame of reference that is independent of Earth's position. Unlike celestial coordinates based on the equator and poles of Earth, galactic coordinates are centered on the galaxy itself. This makes it possible to describe the locations of stars, clusters, nebulae, and even the solar system's motion in a standardized way. For example, when we say a star lies at plus 30 degrees galactic latitude, it is 30 degrees above the galactic plane toward the NGP, regardless of where Earth is located in its orbit. Similarly, the solar system's oscillation above and below the plane can be quantified precisely using these coordinates. It is important to note that the concepts of up and down are inherently relative. While the north and south galactic poles provide convenient directions for mapping the Milky Way, they have no absolute significance in space. Above one region of the galaxy may be closer to the NGP, while in a warped outer arm, up may be several hundred light-years off relative to the local midplane. The galaxy itself is moving through intergalactic space, and all nearby galaxies have their own planes and poles, making vertical direction truly context-dependent. Nevertheless, within the Milky Way, galactic coordinates offer a practical and intuitive framework for describing vertical structure. The galactic coordinate system also helps place other cosmic structures in context. The solar system's position relative to the galactic center, the distribution of globular clusters in the halo, the orientation of the local bubble, and the paths of high-velocity stars can all be mapped using galactic longitude and latitude. The NGP and SGP serve as the ultimate anchors for these measurements, defining the three-dimensional orientation of objects in the galaxy and allowing astronomers to communicate positions unambiguously. From a visual perspective, imagining the Milky Way as a slightly warped disk with the galactic center at its hub, the poles define the vertical axis through the middle of the disk. Up toward the NGP points roughly perpendicular to the central disk, while down toward the SGP points in the opposite direction. As the solar system orbits the galactic center and oscillates above and below the plane, it travels along this vertical axis relative to the poles, moving through the layered structure of stars, gas, and dust that define the disk and halo. In summary, the galactic center and galactic poles provide the reference framework for understanding direction within the Milky Way. Up and down are relative terms anchored to the NGP and SGP, allowing astronomers to define galactic latitude and longitude, map the solar system's motion, and describe the position of stars, clusters, and gas clouds. This coordinate system transforms the abstract concepts of up and down from vague notions into precise measurements, situating the solar system within the galaxy's three-dimensional architecture. By using these references, we can move beyond local perspectives and explore the full complexity of the Milky Way, from its disk and halo to the broader intergalactic environment.
Having established the framework of galactic coordinates with the galactic center and poles, it's vital to grasp the scales involved when we talk about above and below. The terms may seem intuitive, but the distances they describe vary enormously depending on the frame of reference. Being above the solar system by even 1 billion miles sounds vast in human terms, yet in the context of the Milky Way, it is practically negligible. To truly appreciate the three-dimensional structure of our galaxy and the universe beyond, we need to zoom out and compare these vastly different scales, from local distances within our solar system to the immense vertical stretches of the galactic plane, halo, and intergalactic space. Within the solar system, distances are often measured in astronomical units, AU, where 1 AU equals the average distance from Earth to the Sun, approximately 150 million kilometers or 93 million miles. When we say above the solar system by a few billion miles, we might be picturing the outer planets, the Kuiper belt, or even the distant Oort cloud. For example, Pluto orbits at roughly 40 AU, while the Oort cloud may extend up to 100,000 AU or nearly 1.5 light-years from the Sun. Even at these staggering scales for humans, these distances are tiny compared to the vertical thickness of the Milky Way's disk or the expanse of its halo. The difference highlights the immense gulf between local and galactic scales. Stepping up to the scale of the Milky Way, the disk of the galaxy is roughly 1,000 light-years thick, with most stars and gas concentrated within this plane. The solar system, currently located about 25,000 to 27,000 light-years from the galactic center, oscillates vertically above and below the plane by only 70 to 100 light-years. Compared to the radial distance around the galaxy, or the distances to other parts of the disk, this vertical oscillation is relatively small. Yet it places the solar system in regions with different interstellar densities and magnetic environments.
When we describe motion above the galactic plane, we are talking about tens to hundreds of light years, orders of magnitude larger than distances between planets in our own system. This provides perspective. The scale of vertical motion in the galaxy dwarfs even the farthest reaches of the solar system by factors of tens of thousands or more. Beyond the disk, the halo extends even further. Globular clusters and halo stars orbit thousands to tens of thousands of light years above and below the galactic plane. For instance, the globular cluster M13 in Hercules is located about 22,000 light years above the plane, relative to the Sun's position, while Omega Centauri in the southern sky lies roughly 15,800 light years below the plane. These vertical distances exceed the solar system's size by unimaginable proportions. To put it in perspective, the distance from the Sun to Pluto is about 0.0006 light years. The halo stretches tens of thousands of light years, meaning that above and below the galactic plane is about 50 million times farther than the farthest reaches of the solar system. It's a scale so vast that it is nearly impossible to visualize without comparing it to the familiar planetary distances in our own neighborhood. Stepping even farther out, intergalactic scales magnify this disparity even more. The nearest large galaxy, Andromeda, is roughly 2.5 million light-years away. Compared to the thickness of the Milky Way's disk, this distance is 2,500 times greater. And compared to the vertical oscillation of the solar system, it is tens of millions times greater. Distances above and below the plane of the Milky Way, in this context, are effectively local perturbations within a vast cosmic web that stretches across millions of light years. Here, even the halo, with its thousands of light years of vertical extent, becomes a minute structure in the grand tapestry of the universe. It's also helpful to visualize these differences spatially. Imagine the solar system as a grain of sand. The Oort cloud might be a thin layer of dust extending a few meters around it. The Milky Way's disk, a circular field tens of kilometers across. And the halo, a vast cloud spanning hundreds of kilometers. Beyond that, intergalactic space, with Andromeda, the Virgo cluster, and dark matter filaments, form the entire surrounding universe, stretching far beyond what the human mind can easily comprehend. This analogy illustrates how above and below are context-dependent. What is considered far at a local scale is almost negligible at a galactic or intergalactic scale. Understanding these scales is crucial when interpreting observations. For example, a star a few hundred light years above the solar system may seem distant locally, yet it is still very close compared to the vertical distances of halo globular clusters. Similarly, when astronomers map the distribution of gas, dust, and dark matter above and below the plane, they must account for the massive difference in scales, from local interstellar clouds extending tens of light years to the galactic disk's thickness of 1,000 light years, to the halo's thousands of light years of vertical extent, and finally to intergalactic filaments stretching millions of light years. In essence, this comparison of scales provides perspective on the meaning of above and below. When we talk about the vertical structure of the solar system, we're dealing with distances measured in billions of miles, or AU. When we talk about the vertical structure of the galaxy, we are discussing tens of thousands of light years. When we extend the perspective to the cosmic web, we're looking at millions of light years. Each scale provides a different context and understanding of the universe, emphasizing that vertical orientation is relative not only to the local plane, but also to the galaxy and the universe at large. In summary, the concept of being above or below depends heavily on the scale under consideration. Within the solar system, distances are small in cosmic terms. Above the galactic plane, distances are vast, yet still minor compared to the halo or intergalactic space. This comparison helps us visualize the layered structure of the universe, placing the solar system within the Milky Way's disk, the galaxy within its halo, and our galaxy within the broader cosmic web. By appreciating these scales, we can better understand the true enormity of above and below, from billions of miles to millions of light years. Having explored the vast differences in scale when discussing above and below, we now turn our attention to the cosmic frontier beyond the Milky Way, where the universe becomes even more complex and structured. Above and below our galaxy, space is far from empty. It is filled with a network of satellite galaxies, dark matter clouds, intergalactic gas, and cosmic filaments that weave the large-scale structure of the universe. These structures define the Milky Way's environment, influence its motion, and provide crucial context for understanding the vertical dimension of space on intergalactic scales. The Milky Way is surrounded by numerous satellite galaxies, small companions that orbit the main galactic disk. Some of the most well-known include the Large and Small Magellanic Clouds, LMC and SMC, the Sagittarius Dwarf Spheroidal Galaxy, and the Sculptor and Fornax Dwarf Galaxies. These satellites are not confined to the galactic plane. Many occupy positions significantly above or below the disk, creating a complex three-dimensional distribution. Their gravitational interactions with the Milky Way generate tidal forces that pull stars, gas, and dark matter from both the satellites and the main galaxy, forming streams and ripples that stretch across tens of thousands of light years. In effect, these satellite galaxies act as markers and sculptures of the vertical structure surrounding the Milky Way, illustrating that above and below extend far beyond the halo itself. Beyond visible satellite galaxies lies the invisible scaffolding of dark matter. Dark matter clouds envelop the Milky Way, forming an extended halo that dominates the galaxy's gravitational potential. These clouds extend thousands of light years above and below the disk, influencing the orbits of stars, globular clusters, and even satellite galaxies. The dark matter halo interacts with other galaxies' halos, forming the framework for the local group and connecting to the cosmic web on larger scales. While we cannot see dark matter directly, its presence is inferred through the motions of stars, gas, and galaxies, as well as through gravitational lensing effects that bend light from distant objects. At even larger scales, the Milky Way is embedded within cosmic filaments, part of the vast large-scale structure of the universe. These filaments are composed of dark matter, gas, and galaxies, forming an interlinked web that stretches across hundreds of millions of light years. Above and below the plane of the Milky Way, these filaments connect our galaxy to others in the Laniakea supercluster, a massive gravitationally bound region containing over 100,000 galaxies. These filaments not only provide pathways for galaxies to interact, but also serve as conduits for gas inflow, supplying material that can eventually accrete onto the Milky Way, fueling star formation and continuing the cycle of galactic evolution. Between the filaments lie cosmic voids, enormous regions of relatively empty space that extend for tens to hundreds of millions of light years. These voids contrast sharply with the denser filaments and clusters, emphasizing the highly non-uniform nature of the universe. Even above and below the galactic plane, the Milky Way's halo and surrounding satellites occupy only a small fraction of space. Most of the universe in these directions is low-density intergalactic medium, interspersed with sparse galaxies. These voids play a role in shaping the motion of galaxies, as their underdense regions allow neighboring filaments and clusters to exert gravitational influence, gently tugging galaxies into more densely populated structures. The interaction between these satellite galaxies, dark matter clouds, and filaments also impacts the Milky Way's evolution. Streams of gas and stars from satellites can fall toward the galactic plane, replenishing the disk's material for star formation. Tidal interactions with satellites can warp the disk or trigger spiral arm formation. Even the vertical oscillation of the solar system through the galactic plane is subtly influenced by the gravitational pull of the halo and nearby satellites. These processes remind us that above and below the Milky Way are not simply empty directions in space. They are populated by both visible and invisible structures that actively interact with the galaxy over millions to billions of years.
Theories about the large-scale structure also suggest that some dark matter clouds and satellite galaxies may remain undetected, hidden because they are faint or composed primarily of dark matter. Simulations of galaxy formation predict that hundreds of such small companions should exist, occupying positions above, below, and around the Milky Way. Their gravitational influence could explain subtle irregularities in the motion of stars in the disk and halo, as well as streams of globular clusters and tidal debris. These hypothesized structures reinforce the idea that the universe's vertical dimension is a complex and active region, where interactions shape the evolution of galaxies over cosmic time. Finally, cosmic filaments act as highways for matter and energy on the grandest scales. Gas flowing along these filaments can accrete onto galaxies, while gravitational interactions along filaments can merge galaxy groups into larger structures, forming clusters and superclusters. Above and below the Milky Way, these filaments provide context for its motion, orientation, and interaction with the local group. They remind us that the concept of up and down is always relative. The galaxy moves within a three-dimensional network, and its vertical axis, defined locally by the galactic poles, intersects only a fraction of the enormous vertical space threaded by filaments and dark matter. In summary, the regions above and below the Milky Way extend far beyond the disk and halo, encompassing satellite galaxies, dark matter clouds, and cosmic filaments. These structures shape the galaxy's evolution, influence its motion, and connect it to the larger cosmic web. While vertical direction is relative, examining these features highlights that the Milky Way is embedded in a highly structured and interactive environment. From satellites tugging at the halo to filaments guiding intergalactic gas, the universe above and below the galaxy is a dynamic and interconnected space, linking the local vertical structure to the vast architecture of the cosmos. Having journeyed from the immediate surroundings of the solar system through the Milky Way's disk, halo, and magnetic field, all the way out to intergalactic space, it is fitting to reflect on the concept of above and below in the cosmos. At every scale, from planetary distances to cosmic filaments stretching millions of light years, these directions are ultimately human constructs, designed to provide orientation and context. In space itself, there is no intrinsic up or down. Gravity pulls towards the center of mass, but beyond local gravitational influence, orientation is relative. The Milky Way has a plane, the solar system oscillates above and below it, and satellites orbit the galaxy in complex patterns. But these motions occur in a three-dimensional environment that lacks a universal vertical. Recognizing this is not a limitation. It is an invitation to appreciate the universe's complexity.
Our natural tendency to define directions like above and below stems from everyday experience on Earth, where gravity establishes a clear sense of up and down. Yet when we extend our perspective to the solar system, these directions become relative. Above the ecliptic plane is simply one side of the planet's orbital disk. Above the galactic plane is toward the North Galactic Pole, a direction defined purely for reference. Even beyond the Milky Way, in intergalactic space, verticality has no absolute meaning. Cosmic filaments, voids, and clusters exist in all orientations. By embracing this relativity, we gain a more accurate understanding of the three-dimensional architecture of the cosmos. Exploring what lies above and below our solar system highlights the layered structure of the universe. At a local scale, the solar system is nested within the local bubble, a hot, low-density cavity surrounded by clouds of interstellar gas. Zooming out, we move through the galactic disk, where stars, gas, and dust occupy a plane that is slightly warped and undulating. Higher still, globular clusters and halo stars orbit above and below the disk, embedded in a spherical halo dominated by dark matter. Beyond the galaxy, satellite galaxies, dark matter clouds, and cosmic filaments form a vast interconnected network that defines a universe on the largest scales. By understanding these layers, we can see that the universe is not flat or uniform, but richly three-dimensional, with structure and dynamics in every direction. The concept of direction also deepens our appreciation of motion and perspective. The solar system orbits the galactic center at incredible speeds, oscillates above and below the plane, and travels through regions of varying interstellar density. Stars in the halo follow elliptical orbits, globular clusters trace vertical arcs, and satellite galaxies interact with the Milky Way's gravitational pull. At intergalactic space, the Milky Way itself is moving within the local group and toward the Virgo cluster. At every level, motion occurs in three dimensions, reinforcing that spatial orientation is context-dependent. Up for the solar system is different from up for a star in the outer halo, and both are dwarfed by the vertical scale of cosmic filaments. Understanding these perspectives also helps visualize scale. Distances that seem enormous locally, like 1 billion miles above the sun, are minuscule compared to the tens of thousands of light years separating the disk and halo, or the millions of light years between galaxies. Comparing these scales illustrates the incredible breadth of the universe and our place within it. From our vantage point on Earth, we are privileged observers of a dynamic, structured cosmos where up and down are not absolutes, but useful ways to navigate and describe the vast three-dimensional expanse. Ultimately, exploring what lies above and below the solar system, and by extension the Milky Way, is more than orientation. It is about understanding the nested hierarchy of cosmic structures: planets within solar systems, stars within the galactic disk, clusters within the halo, galaxies within filaments, and filaments within the cosmic web. Each layer informs the next, creating a coherent picture of the universe's architecture. Recognizing that above and below are relative allows us to transcend earthbound notions of verticality and engage with space on its own terms, a dynamic, multidimensional reality that is as beautiful as it is complex. In conclusion, while the human mind naturally seeks directions like above and below, the cosmos itself operates without inherent up or down. Yet by defining these directions relative to the solar system, the Milky Way, and the broader universe, we gain a powerful tool for exploration, understanding, and imagination. From the local bubble surrounding our sun to the dark matter filaments connecting galaxies across millions of light years, the universe reveals a rich three-dimensional structure that is both intricate and awe-inspiring. These concepts remind us that our perspective, though relative, allows us to navigate and appreciate the universe in its full grandeur, turning abstract directions into a roadmap for cosmic discovery. The journey above and below the solar system is, in essence, a journey through space, time, and scale, connecting the local neighborhood of the sun to the farthest reaches of the cosmos. It reveals that the universe is not merely a flat backdrop, but a living, three-dimensional tapestry where each layer, from planetary systems to cosmic filaments, contributes to the intricate whole. By exploring these dimensions, we cultivate a deeper sense of connection with the universe and an understanding of our place within its vast, layered, and beautifully structured expanse. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.